Hello, everybody. My name is Marc Swinnen. I'm a Director of Product Marketing at Ansys Semiconductor, and I will want to welcome you to this panel discussion. I will be the moderator today for this roundtable. And the topic of today's discussion is your hardware secure in a zero trust environment? Let me start by introducing our three speakers. So we have Mikael Rien, Senior Principal Security Architect at ARM, where he designs countermeasures against physical attacks. Mikael has extensive experience developing interface IP, analog IP, and ESD solutions. Previously, Mikael worked at ST Microelectronics. He holds 20 patents and a master's degree in electrical engineering from ENSERG in Grenoble, France. Our second speaker is Dr. Jason Oberg, co-founder, CTO, and director of Tortuga Logic, where he's in charge of the company's technology and strategic positioning. He's a leading expert in hardware security whose work has been cited in over 1,000 times and holds 7 patents. He received a bachelor's degree in computer science from the University of California in Santa Barbara and a master's and doctorate degree from the University of California in San Diego. And our third panelist is Dr. Norman Chang, who is co-founder of Apache Solutions and is currently a fellow and chief scientist at Ansys. He has authored over 50 papers, holds 18 patents, and is a committee member at ESDA and on the AI/ML advisory board at SI2. He received his doctorate in electrical engineering and computer science from the University of California in Berkeley. Now that you've met our panelists, we will start the discussion with a very brief introductory presentation from each of our speakers. And after that, we'll tackle some important questions in an open debate. First up is Mikael Rien from ARM with an overview of hardware physical attacks. Mikael, over to you.
Okay, so now focusing only on physical attacks. I have put them in 3 categories. The non-invasive attacks are only observation of the circuit, so you're measuring something. With semi-invasive attacks, the intent is to modify the behavior of the chip with respect to its response. And finally, the invasive attacks require a physical modification of the circuit, example of a fib. A bit more on the non-invasive attacks, Here I'll focus on side channel. In cryptography, a side channel attack is based on the information that you can gain from the physical implementation. The most common ones are power and EM analysis. They are also the easiest to conduct in the physical attack space on a non-protected device, that is. If the device is protected with suited countermeasures, the effort and the cost is going to go up, of course. You'll need more material. You'll probably need a more skilled attacker. I put the EM analysis in the same category as power analysis, very similar. Although it could seem fancier, it uses the same material, similar scripts, and only need an additional EM probe to your bench. Now on to the semi-invasive attacks. So here the goal is to derail the circuit out of its normal behavior. We want to create faults compared to an expected output. These faults can then be exploited either to bypass some instruction or some boot sequences. It could also be used to extract keys from a crypto system through DFA. DFA stands for differential fault analysis. I list here some examples of how these faults can be created. There's the out-of-bound attacks, where you can change power supply and temperature of a circuit out of its normal environment or normal bounds. Optical and laser pulses can also be used. You need a bit more material to do so, but it's not out of reach. There's also EM fault injection. It's different from side channel EM, where you measure the emission. The EM emission here, you inject EM into the circuit. And we also have other possibilities like injecting glitches on the power or injecting current in the substrate, which is PBI. In terms of invasive attacks that require modification of a circuit, the most common one is around the use of a fib. a focused ion beam. With laser cuts, you may modify the functionality of a circuit, or you can even position little landing pads to measure critical internal signals. This is not exhaustive. I could have also talked about reverse engineering, where you could delay a circuit in view of extracting keys for creating counterfeit products, for example. Okay, and on to the next. This here is my summary. So to summarize, I have here again the three physical attack families listed again. Here the cost of the attack is decreasing from high to low. The non-invasive ones are the most relevant usually. They're at the reach of a simple hacker. Fault injection attacks have been shown to need not too much expensive equipment. And at the end, the costlier ones at the top, the invasive ones that need a complex material. So once again, we're back to an effort and cost of attack versus the value that the attacker is going to extract from it. So that's all from me.
Thank you, Mikael, for that introduction. And we will now move on to our second speaker, which is Jason Oberg. He will be from Tortuga Logic, and he will be talking to us about detecting and preventing hardware vulnerabilities pre-silicon. So over to you, Jason.
Great. Thank you so much, Marc and Mikael, for the first couple of presentations here. Let me jump right in. I think, this, as Mikael focused on in his introductory here on a lot of the physical attacks, I'm going to talk a lot more about some of the more remote and digital attacks, specifically looking at vulnerabilities in architecture as well as in software. And just some perspective, Mikael highlighted some of the physical attacks that have happened, but there's been a pretty significant increase in hardware-based vulnerabilities in the last several years. This chart I show here at the right, on the bottom x-axis is just year, and then the y-axis is the number of hardware vulnerabilities. And this is data that's been pulled from the National Vulnerability Database. And so you can see this big trend and spike here in the last several years, starting around 2016. And really that's been happening because of the increase in complexity of modern semiconductors, right? So the modern SoC is a very complex hardware software system. And that's basically resulting in a lot of hardware-based vulnerabilities. We also see this trend of actually focusing on hardware, because if you actually find a hardware vulnerability, you can actually break into an entire system. And so really the ROI of finding a hardware vulnerability is quite high. This is the case for both physical type of attacks as well as things that can be done more remotely. And then interestingly enough, there's an enormous shift to add more security features into hardware. There's a big initiative around roots of trust, really rooting security and storage into hardware. But what's happening is there's actually, due to the first point there of increased design complexity, by actually moving more security features into hardware, it's actually making hardware more vulnerable to these types of exploits. And so we see this really interesting trends going on. And there's been a lot of real exploits, in obviously within the physical domain. Mikael highlighted several of those, but in the less, non-physical domain, there's been a lot of hardware-based vulnerabilities. And so one example here is this Nailgun attack that affected a lot of debug infrastructure in a lot of ARM-based SoCs. We've, in the early, I think in January 2018, we saw the meltdown inspector type vulnerabilities, which exploited some microarchitectural side channels, specifically targeting a lot of the application processors that the industry uses. We've seen vulnerabilities hit Bluetooth or energy devices, for example, SoCs from TI, this bleeding but vulnerability. And we've seen issues with respect to roots of trust. And for example, this vulnerability called ThingryCat, which affected a lot of Cisco routers and their root of trust FPGA system. And so there's been a pretty significant amount of growing hardware vulnerabilities exploiting a lot of the low-level architecture and software misconfigurations of a lot of these systems. And really, one very important component of that we all need to remember is that security is a system-level problem. It's really hard to work on security in silos, and actually, in practice, it's impossible to build systems effectively by working in silos. And really, if you look at a modern SoC, vulnerabilities can hide in complexity of the interfaces and interactions of system components. So, as you know, a modern SoC has very complex hardware blocks. So within a respective IP core, there could be security concerns. As you actually stitch a lot of those IP cores together into a larger system, there's a lot of hardware misconfigurations that can go on. Things can get unconnected properly. We've seen customers incorrectly ground privilege bits and escalate privilege accidentally. And then there's obviously the whole system software configuration. As the system boots, as the system gets configured, that also introduces a lot of potential problems. And so it's really important to look holistically about the entire system. And so some goals to think about that I'll talk about here throughout the rest of the panel is that you really want to ensure that you don't have vulnerabilities at the actual hardware implementation level. So you really need to think of this design, the secure development lifecycle, where you're actually looking at block level to system level to actually the full system here. And so you want to make sure there's no vulnerabilities at the actual IP block level. You want to also make sure that you don't introduce vulnerabilities at system integration. So, for example, improper management of debug and test interfaces. Like I said, we've seen customers actually accidentally ground privilege bits at the system interconnect level, and then also very importantly at the system level, making sure that the software is properly configuring the different features. So the assets that are being used in secure boot, like encryption keys and your boot image, making sure you've securely configured memory protection units. And then, various different access control configurations at the system interconnect level is also very important. And so the general theme that we'll talk about here, at least on the Presilicon side, is that a lot of this whole notion of creating a secure development lifecycle is something that's well established in the software domain. I think it's important to adopt those same types of best practices to, as Mikael mentioned, really to help reduce risk at the Presilicon stages. So while you're going through your hardware design and architecture requirements to block and subsystem design to your whole SoC integration and testing, you can build a good secure development lifecycle across that with threat modeling, block level security verification, and system level security verification. And then this is a necessary infrastructure to help enable the broader secure development lifecycle, which would include Postsilicon analysis for security. And so with that, that's my brief introduction. I'll hand it over to Marc and Norman.
Thank you, Jason. That was a great overview. And I'll now pass over to our third speaker, Norman Chang from Ansys, and he will introduce us to simulation-based side channel emission analysis. So over to you, Norman.
So currently, the side channel security simulation in the market, there's almost no solution. And if you want to do simulation based for security, it's a lot of challenges. First, you have to be able to run long vectors, which means thousands or millions of payloads. And then you need to have a very accurate solution. And also the sampling points in the time domain needs to achieve maybe 10 sampling points or up to 60 sampling points in each cycle. So it's a big challenge. And if you look at the next slide, there are quite a few side channel attacks, as mentioned by Mikael. There's a power emission attack, which is a traditional power measurement that people can do. And however, for the dynamic voltage drop analysis and the electromigration analysis, and that Ansys have a industry standard tool called Rien for power noise emission analysis that can produce dynamic voltage drop or electromagnetic simulation. So we have an opportunity to provide this simulation solution to handle the power noise for side channel attack, and also the electromagnetic in terms of the magnetic field on top of the chip. And that also can address the thermal emission and other kind of attacks. If we move to the next slide, for power noise side channel emission analysis, what we mean is that for the long vectors with fixed key and thousands of payloads or millions of payloads, we will be able to simulate the current on every wire segment on the top metal layer And also we can get the dynamic voltage drop on the top metal layer wire. And from there, we are looking at the location-dependent variation from the power noise in terms of the current or in terms of the dynamic voltage drop. And we can look at the T-scoring, the KL divergence, or we can derive the key from the simulation-based minimum number of traces to crack the key. And if users are able to fix the design with a different kind of countermeasure techniques, then we can provide a simulation again. So on the right is the collaboration work with the Kobe University that we do a lot of measurement correlation. And you can see that from the simulation compared to the measurement, the simulation solution can achieve the MTD with a less number of cycles compared to the measurement, because the measurement would be able to see more system noise. So if we move on to the next slide for the electromagnetic side channel emission analysis, that the challenge is that we have to be able to calculate the magnetic field for thousands of cycles, accounting for all the millions of wires on the AES or with the embedded AES in the SoC. And this is a big challenge for the simulation workload. And we should be able to do that if we want to achieve a simulation-based side channel analysis. So this pretty much summarizes that the challenge for providing a simulation solution for side channel emission analysis. Thank you.
Thank you, Norman. That was a very detailed overview there of the physical attacks. We'll move over to the open discussion part of this panel now. And I'd like to start off by saying that it looks like there's a lot of possible avenues for attack, a lot of different techniques, a lot of vulnerabilities, a lot of ways to mount an attack. And we probably can't protect against every last one of them, which then leads naturally to the question is, which one should I be most concerned about first? Which ones are the highest priority, and where should I put my effort into first? Which vulnerabilities are the most important right now? And maybe, Mikael, if you could start off with that one.
You need to know which one you need to protect against. And maybe sometimes a good way of starting with that would be, I was thinking of PSA, the platform security architect that you can find on our website, which kind of, the first step is to analyze where you are. So looking at what are your assets, what could be your threats, and then you move on to know what you need to put as protections in your circuit.
Jason, do you have some views on this?
Yeah, no, absolutely. I think, the prioritization of what security concerns are of most importance is really goes back to the whole process of threat modeling and realizing that security is a system level problem. Because if you look at the context of where your SoC is going to be deployed, if it's in a context in which there's a lot of physical access to the device and the actual, maybe the code base that's running is relatively simple, then obviously physical attacks are going to become more prevalent. If you look at a model where, the silicon is in a data center and it's, guarded by physical infrastructure security in some respects, right, where the actual servers are locked, you're going to be looking at more remote-based attacks. And so going through that process of really looking at the system, what an attacker can actually get accomplished with respect to that system, and then drilling your analysis down from there. And then also you have to look at the type of attacker, what resources they have available. I mean, Mikael mentioned in his presentation, doing power-based side channel attacks you can do with a relatively low-cost equipment, basic oscilloscope and some open source attack software. And so mitigating against that is in an environment where there's physical access is something that you should do at a bare minimum. But as you get into more complex attacks, looking at very, very focused fault injection type of attacks on a very complex, 7 nanometer SoC, for example, those become a lot harder. But if obviously if you're fielding your silicon into an environment that is of concerned against nation state attacks and these types of things where there's a lot of money that can be thrown at the problem, then you have to mitigate those to mitigate against those as well. And so it's not a hard line of what's the most important. It really goes back to that whole process of threat modeling, looking at system from a security perspective, and then drawing your conclusions around what mitigations you need and what you should protect against from there.
So Jason, you cite a number of real-world examples in your presentation, and I'm wondering what applications or customers care most about this. So is it just the military, or does the commercial market care about this as well? So what is the target market that will pay extra to have more security in their chips? Is every user equally a target, or are there particular applications, particular customers that are willing to, spend extra money to get this done?
Yes, I mean, I think the way the biggest drivers that we've seen for security are really ones that have been burned. So if you've been hacked, then you kind of understand the pain with respect to not addressing it ahead of time, or there's some sort of standard or compliance that has to be met. In the government side, it's obviously very much more driven by compliance. Their tolerance for risk is very low, and so I think that's a very clear market for where these capabilities are needed. But if you look at other systems that have very high cost of, the criticality is very high, the tolerance for risk is low, markets like automotive, as well as industrial IoT type applications. It's hard to generalize IoT because there's certain segments of IoT that are very simple and don't have a lot of impact from a security perspective. But the ones that, with respect to critical infrastructure and so on, we also see a lot of very strong security concerns there. And so it's really around, the risk reduction. And a lot of those markets are making big investments. We see a lot of enhancements and deployments of roots of trust and adding a lot of security features into hardware. And related to that, we see a lot of drivers from the end customer, in automotive, for example, the OEMs and so on, looking at, asking the questions of how have you implemented security? How have you validated this? Can I trust your feature sets? And I think that trend is going to continue to grow here.
And Mikael, does ARM have a view on that?
Being able to simulate in some way your security level is going to become more and more important. And one example is a little bit what we've seen on the simulation-based side channel emission. I mean, that is something promising. If we're able to upfront look at what is going to be the level of security, I mean, it's much more better than waiting for silicon to come back and see where you are.
Thank you. So there's a lot of designers in our audience, and I'm sure they are curious about to what degree can we rely on simulation, upfront simulation, to catch these vulnerabilities, as opposed to actually working it out in a physical lab. Can we rely on these simulations? Are they complete enough? Are they reliable? Maybe Norman, you could lead us in on that one.
Yes. If you look at the market of the dynamic voltage drop about 10, 15 years ago, I co-founded a company, Apache Design Solutions. At that time, people did not trust the simulation at all. And security, I think, is at in terms of the current status, is at a similar status compared to 5, 10 years ago. That because simply speaking, you cannot wait for the design to come back and then you do the measurement, try to crack the key, and suddenly you found a weakness in the security vulnerability, and it takes too long to go back and fix the design. And simulation is essentially a solution to avoid that problem. So from our experience that we are trying to work with the customers such as ARM or other companies, try to understand their countermeasure design. And we have known a lot of simulation techniques in terms of the voltage island, frequency variation, randomness in the masking. And we can possibly do all kinds of simulation from that regard. So in terms of simulation technique, I think we have a much higher confidence that we can address security, not only for the long vectors, but also with the different kind of countermeasures that we will be able to do the simulation. However, we still need to work with the customers so they can open up a little bit about the countermeasure design. So we are able to devise the new algorithm and to do the simulation smoothly and also with a robust way.
Thanks, Norman. So, Jason, Tortuga does a lot of simulation-based analysis too. Do you see this as a complete solution that people can rely on, or is it just one factor? You still have to do hardware testing.
Yeah, so I would always view the this notion of a secure development lifecycle. A very important component of that is actually being able to assess the security of the final system, and so both simulating from a physical perspective as well as on the digital side for security vulnerabilities is going to help dramatically increase your, decrease your risk profile, increase your assurance and your confidence level on the result of the resulting system. But it's not a replacement for actually doing the post-silicon analysis. And the reason that's important is because the assumptions you make, during design and during simulation may not be valid. Or maybe you'll have taken a limited scope or not looked at all the corner cases for when the actual system's deployed. And so I think it's important to use that as a way of really bolstering and improving the whole process. And in security, there's a whole process of white box and black box testing, where black boxing, you don't have much knowledge of the internals. The post-silicon analysis is very much a black box test, and that's very important because you can merely put your mindset into what the attacker will actually have access to, and so it's really important to still continue to do that. But obviously, the white box testing that you can do pre-silicon and during simulation, by having full design knowledge, allows you to get really, really fine-grained analysis of where potential problems may be. But I don't think one is a replacement for another. I think the big issue that the industry has right now is that it's only black box and only post-silicon, which really heavily limits your ability to find issues early on, as Norman mentioned. It's way better to find issues early so that you can fix them. And then also that will help you build more of a robust product. So it's, there's a very large opportunity, I think, with respect to the type of vulnerabilities that you could find during design. We're working on an important component of that, looking at more of the digital and software-based vulnerabilities, but expanding those in the physical domain and expanding those into both physical side channels as well as EM and these type of things that Norman mentioned, I think are really important opportunities.
Thanks, Jason. So we're slowly running out of time. So maybe one last question. Engineering is all about trade-offs, and I'm sure that hardware security is no different in that. What are the trade-offs need to be considered when looking at mitigation of hardware vulnerabilities? I mean, is it just more time and effort on the design side, or is there an impact on power, on performance, on area, on reliability? Are there other costs that will be incurred by improving security? What are the trade-offs? Maybe Mikael, if you could start on that one.
It's a tough one, Marc. So trade-offs, of course, you're going to have to. I mean, security doesn't come for free. You're going to have to spend effort. If I look on the side channel side, you're going to need more power and area, definitely, if you want to put in place the correct countermeasures against EM and power attacks. So that's why it's important at the beginning to know what is the level of security you need to target depending on your market, so that you don't put the barrier too high, because you're going to have to pay a penalty. Security is going to come with a cost at some point.
Norman, thank you, Mikael. That's an overview. And Norman, do you have a specific view on the cost or the penalties or the trade-offs maybe at the physical implementation level? Extra metal, extra dummy gates, anything like that you typically will have to pay?
Yes, we work with essentially a lot of customers, right, for dynamic voltage drop fixing or electromigration fixing. So for the security, they have to consider power, performance, area, or even including thermal signatures. And for different applications, they have a different level of sophistication for the countermeasure design. So again, for the simulation technique to work, we have to understand the design a little bit, and from working with the customers closely, and for different applications that need. And some of the techniques that we see from customers are very sophisticated, and that presents a next level of a challenge for simulation for security application. That also is a very exciting challenge because we don't see that in the regular design. So for the security design, it's another level of sophistication in terms of the design technique that make my work every day very exciting. Thank you.
Thank you, Norman. And for the final word, I'll move to Jason. Do you see any trade-offs there, impacts on power and performance in area from the front-end design side?
Yeah, no, so I think the way to always think of this is that the more you make security part of a process, the less impact that you're going to have with respect to both the overheads in terms of power, performance, and area, as well as the time and effort. I think what often happens is that you'll take one of the classic vulnerabilities, whether it's Meltdown or Spectre or some of these side channel vulnerabilities, and a mitigation will be added more broadly, right? We saw the performance impacts that Meltdown and Spectre had, where it really dramatically reduced performance. A lot of the mitigation techniques for side channels really are more holistic. You buy an entire mitigated root of trust or an AES engine, for example. But if you actually use a process which focuses on what threats you're trying to prevent against, and you kind of build that into your process, you can actually sprinkle mitigations and focus your efforts in a way that dramatically reduces the power, performance, and area type of overhead. And then because it's part of the process, there's actually a lot less of a time sink in terms of the actual time and effort put into this. And I think there's good ways of building that secure process in to make security as part of the core design practice, so that you can actually release a secure or more secure product without heavily degrading, power, performance, and area. Because I think there's, like I said, a tendency to say, I need security, so I'm going to buy an IP core, I'm going to add this mitigation, whether it's in hardware or software, and those can be very impactful. And so I think if it's more methodical, you can actually do so in a way that's less impactful.
All the speakers, and this is a very broad subject. We can go on for hours, but I hope this has piqued the audience's interest in this subject, and there's definitely more out there to be learned. And I would thank all our speakers again and say bye, and see you next time.